Hi, thank you so much for coming to my session. I really appreciate you taking your time. My name is Lita, and I'm here to talk to you about distributed tracing. I work on the networking team at Lyft, and these are one of the main observability tools that we use to look into what's happening with our system. And I hope at the end of this talk, it's mostly meant for people who are not really experienced with distributed tracing, or they don't have it quite yet and they want to know what it is. And at the end of the talk, I hope that you have a good idea of what it is and then you can take it with you into your work at your company. Before I dive into what tracing is, I want to give a little bit of background about myself. So I worked at Lyft 4 years ago. And I started off as an application developer working on Lyft Line just when it launched. And so I built a lot of features there and helped it launch to nationwide. And then after a year, I switched into infrastructure. And there, I would help decompose our monolith to microservices, but also decided to go into code generation and trying to make communicating between microservices a lot more efficient and a lot more easier. And we use protocol buffers to do that by generating a bunch of code for a lot of different languages, which is pretty fun. Before then, I switched into networking and got into distributed tracing. Before all of that, before I joined Lyft, I used to work at DreamWorks Animation, creating tools for artists and different production tools for specific movies. And I've also worked on Madagascar 3, which is the most popular movie I worked on. And overall, throughout my career, I think I'm really motivated by making really useful developer tools and making people more productive. And that's why I got really excited about tracing, because I think it enables people to discover data and figure out where to put their efforts. So this is the overall agenda for the talk. I want to start off by giving an overview of what distributed tracing is. And I start off with the visualization aspect, why the UI is really cool and how it displays data in a different way than metrics and logging. And then I go into how to add this to application. So what does the instrumentation code look like? How does the data get collected? So there are many tools out there, but I'll describe one way to do it. And there are many ways, but they're all kind of have similar. They're kind of architectures and similar similar. They're all similar in collection and instrumentation. And then the second part of the talk, I go into how Lyft integrated, because we didn't really start off building with tracing from the ground up. We actually migrated towards it. We had a lot of microservices, and trying to integrate them as a mid-sized company had some interesting challenges and some learnings that I wanted to pass off to you if you decide to go on this venture. So before we can go into distributed tracing, I wanted to give context of what we had before and the current observability tools out there. So first and foremost is metrics. This is the main way that Lyft engineers monitor their services. They're very cheap. You fire them off on your application. At the bottom there, I have a little snippet of Python code that shows how you would fire off a stat, like a counter. And usually we use this to measure error rates, network saturation, throughput, and CPU and memory usage. And it's really, they're very cheap to store. So as your system scales, since you're incrementing a counter, it doesn't get any more expensive. And what's really nice is that when you look at a graph, you can see change, and it's really easy to see anomalies. So people really love their graphs and watching them as they deploy or watching them day to day and seeing if there's any issues. The second form of observability tools that Lyft uses was logging heavily. So we ingest them into Elasticsearch and search out of Kibana. It's very typical. And at the bottom, I show you how one would instrument in an application a log. And this is very useful to triage. Once you see a problem, you go into your logs and search for errors and see what's happening. And they're used to to display stack traces as well as unexpected code paths. So it was more of like metrics and loggings work together, where we would monitor looking at just dashboards, but then go into logs to figure out what's wrong if something was to go wrong. So this talk is not about why, like how distributed tracing is like better than metrics or logging. It's not about that at all. I think they're great. The metrics and logging are really great tools, and they're not going away at all. But the issue with these tools is that they tell a story from the perspective of one application. So you have you have to have a lot of context of that application to get the most out of these tools. And this actually worked pretty well, because especially in the early days of Lyft, when we were a big monolith. So transactions happen in the same computer. So all the request response was contained in one process, and you could stat and log and debug from that perspective. And since it's coming from one application, that worked perfectly well. But now, as we move towards like a microservices architecture, that was no longer the case. So now requests can go through multiple computers, go through multiple network hops, and all the observability data is coming from many different sources. And for a while, we added a request ID or a write ID to kind of tie that data together in our logs to kind of solve this problem. And like be able to aggregate that way. And so I wanted to go through like an example of what that looked like when we started moving towards microservices, how an engineer would debug an issue with that method. This is a common flow I used to do in the early days of Lyft, where like, let's say a client reported an issue or like a support ticket, or like there was a spike in 500s, I'm trying to figure out what's going on. So I would start off with searching by that, like I would be able to find a write ID that it affected and search by that write ID. And then I noticed that like, okay, these are the microservices this is talking to. Like it is bucketized by ASG. And then I noticed that like these are the timestamps. And it goes from like newest to oldest. So I can see here that this request started talking to our front proxy, which is Envoy, and then went to public API, and the RISE API, and the API service. And this is essentially I'm forming this kind of a service dependency diagram in my mind. This is kind of what's happening in my brain to connect all the pieces. Like, okay, this is the flow of the request. This is what's happening as I'm debugging through. And this kind of worked pretty well for a while, especially when we were like only 10 services. However, now we are no longer 10 services. We are now 900 services. And a request can go through 20 and 30 of these things. And one request, it's very typical to have like 200 plus RPC calls. That's very normal. And if I were to continue the way that I was debugging before, I would just be shifting through a bunch of logs, like pages and pages of logs, which is not really a great use of my time. And so, even if, like, so, again, this is way too much to fit in my brain. Like, there's no way to, is there a better way to display this data and that shows me what I care about? And there are certain answers to this with logging, right? So you could learn you could learn the query language to query just for errors, but still like think questions like, what services does this request depend on? Or like, where are what service is taking the longest? Like out of this whole request, the latency is really long. Which one is the bottleneck here? Those are harder questions to answer with logging and metrics. You kind of just have to like, it feels like those tools are not designed to answer those kinds of questions because they're designed to show you data in the perspective of the application, not necessarily the request. So that's what distributed tracing is trying to solve. It's trying to create a different kind of tool where it shows you the data in the request in mind, not necessarily the application. So here is a trace view, that same trace view from the logging turned into a distributed trace. And I've I'm like hiding some UI elements here, like the metadata that shows, but ultimately this is essentially it. And so I want to get through some vocabulary terms before I move on with the talk. So this whole view is what's called a trace, and each row is a span. And here where you see that Envoy emitted a span, and a span contains timing data, so it always has a start and an end time, and it's known as a unit of work. So there's an operation name, and the operation is called egress, so it like sent off a request, and it has a component name, which is the service name. In this case, in the top one, it's Envoy. So it fires off a span, and within that span, it fires it called public API, so it creates a nested span called public API, and then as you can see, it calls nested spans further down. And in Lyft's case, we create a span for both ingress, which is the network coming in, and the egress call out. And what's nice about this view is that it's latency in mind, so the longer the span, the longer the request took. And the spans are tied together by span contexts. So I would like to think of it as a graph, like a DAG, so a directed acyclic graph, where each node is a span, and they are tied together by these span contexts, which is essentially an identifier that ties them together. So here is a more simple example that I made in order to reiterate some examples of why this view is very useful. So we have a client and a web server, and this web server talks to two small microservices and does a database call. And here you can see the client is the root span, and that could show you how from the client's point of view, how long the request response took. And the web server, its work contains like calling the auth service, and then calling the billing service, and does some concurrent processing, concurrent work, and then writes that result into a database. So let's say let's say the client reported 500s, and you're trying to figure out why. With this view, you can there's a way for you to mark that span as an error, and it'll just show up as red. And with this, you can easily see that, oh, something's wrong with the database. I could go investigate. I could go look at the logs for that database to see what's wrong. Versus when the client reported 500s, you look in the web server, be like, I don't see any errors in my code. You have to go searching for them in the logs. It's a lot harder. It takes more energy to figure out where the root problem is, versus this view shows exactly where you should focus your efforts. The second useful thing that I've seen at Lyft that tracing is very useful for is doing these performance optimizations. So let's say you're exploring around and looking at different traces in your system, and you see that the billing service is calling the user data repeatedly 3 times, and it's that exact same user data. So here you realize, oh, that's not very efficient. We could do some optimizations here so that we should introduce some caching so that we don't call the database 3 times. So those are the kind of things that tracing affords, where you can explore the data and see these weird patterns that people add as code changes so frequently. You can easily see optimizations like these that you can make to your service. So yeah, these things are great. You get root cause analysis, you get service dependent. You can see what the services that the request depends on. You can see you can do some performance analysis here. How do you add this to the system? It must be very expensive, or very hard to, or must be very time consuming to add. And there are some couple of challenges for adding instrumentation at Lyft. The biggest one is the fact that we have a polyglot microservices architecture. So we support services in Go, we support services in Python, Java, and PHP. Secondly, we ideally don't want product engineers to think about instrumentation or have them do the instrumentation. The main reason for this is that it's really hard to get them to change their code, especially if it's not for the purposes of building the feature, because they're incentivized to ship product features. And secondly, if they don't see the immediate benefit, it's hard to sell them on. And unfortunately, fortunately or unfortunately, traces get more useful as more services instrument with them. So if like one application instruments with tracing, that's not as useful as if everyone does. Similar, it's kind of like a network effect where like for the typical example is the telephone. So if like I only have a telephone, it's not very useful. But if everyone has a telephone, it gets exponentially useful. We also don't want engineers to make mistakes, especially with timing and like the naming. We want to standardize how you name things. Like you want the component name to be the service name. You want the operation to be a representative name that like is easily searchable without necessarily the engineer knowing what your code looks like. And we really like, how do you enforce standardization with these things? So like again, like the ideal scenario is that not everyone needs to know what your application is doing, but they can still find usefulness in your traces and kind of infer what that span is doing. And so another thing that people have brought up is you could monkey patch. So like that doesn't really work in Go, but in Python and Java, you can inject code, or you can monkey patch how you process a network request. But unfortunately, that really doesn't scale because one, like if there's errors or bugs in that code, like it's hard to figure out what's going on. And product engineers don't like things changing from under them. It's not an ideal situation. And when you're trying to ramp up new engineers to work on this code, it's harder to teach them what's going on. It's better to be more explicit for maintainability. And lastly, we don't want vendor lock-in. So there's many tracing tools out there. The one I just showed you is Lyft, which is the paid provider we use. But there's open source options as well. So like we don't want to be locked into one instrumentation and then like that's what we're stuck with for the and like to migrate over would be painful. So ideally, we want a way where we can like pick and choose depending on like what the needs of the business are. So that's what open tracing is trying to solve. So open tracing is a specification or an interface that you use so that your instrumentation code doesn't change. And then you swap out your vendor in your initialization step. What's nice about this is that it creates a standardization for the data model. And because it's an interface, you're forced to give it the start and end timing information, as well as the operation and component names. It's open sourced. It's supported by the Native Cloud Computing Foundation, and it has a lot of activity. So they have support for many languages, and especially all the ones that Lyft supports, such as Go, Python, and Java. Yeah, so I mentioned that. And what's nice is also it's vendor neutral. So what it does is that it creates an interface between the application of how it's instrumenting and sending data, and then it has an interface for the vendor side to collect the data. So as long as both parties adhere to the interface, they play well together. So I have an example here for in Python of how one would instrument with open tracing. So first, when you start up your application, you would initialize your tracer like so. And I have two examples of initializing the tracer in two different ways. One is through the Lyft collector, and the second is the Jaeger tracer tracing tool, which is an open source tool. And then this is the actual instrumentation portion. So we have like a simple endpoint called -format. And this 3 lines is the only tracing code you need to this is the only like open tracing code that you need to add into your code that's like required. So here what it's doing is it looks at so how it passes that identifier, that span context, is through network headers. So it looks at the headers to see if there is one. If there isn't, that means it's a root span. So it will start up a new span. And it will start, this is specific to Python, but basically anything within that, nested in that with statement is timed. So it'll start up the span, calls format, and it'll pass in the span context if there is one. And that way, that's how it stores that parent-child relationship. And it's not actually, and then there's extra options. So you could add metadata to that. You could add metadata as well. But for the most part, that's all that's really required to emit a span, which is not that much code. And here is like an example of the Jaeger architecture, where basically you have the application, the instrumentation code, and for Jaeger they run a little agent on the side as a sidecar process, which then sends the data to the collectors, and they store their tracing data in a Cassandra database, and the UI just makes queries directly from that database. And this is pretty. This is kind of typical for most tracing tools. Some use Kafka to like ingest the data, and then the Kafka will publish that data to a collector. But for the most part, the data goes to a collector and then stores that in a database, and the UI queries it directly from the database. And what's really powerful is that the application has no idea what client you're using. It doesn't really care. You could swap this portion out with anything else. And like with Zipkin or Haystack or Lightstep. So that's pretty powerful. However, so it's not that much code that's required, but you still have to get engineers to edit application code. You still have to get them to for every endpoint add these spans, or if someone forgets to do that, then that relationship is broken, is not as useful. Is there a zero-touch implementation that's possible? Is there a way for no one to edit code and still get the benefits of tracing? So so at Lyft, we did this by using Envoy. So Envoy is like a proxy, a network proxy that is run on every box. We use it as our front proxy, but also we use it as our proxy into for every service. So this is a sidecar C++ application that's run on every host or every container, and all network requests go through both egress and ingress go through Envoy. So database calls go through Envoy first, and then gets called the database or goes to the application. So here's kind of the rough architecture diagram of how it all fits together. So Envoy is the program that's emitting the traces, and the application doesn't have to do anything. And then when the application makes a call to another application, it just needs to send this header so that they could tie the spans together. And this is abstracted away with network libraries. So we have Envoy client libraries for every language, and all it does is just, if it sees the OT span context header, it will take that and pass it along with the network request. And then Envoy emits all that data via gRPC, sends all that data to the collectors in a very efficient way, asynchronously. So when we roll this out to, when we enable tracing, we just added in one code base and rolled it out. And then everyone, all the services got tracing that were useful right away. It's just and if people wanted to add more like detailed spans, they could do that with a custom, with open tracing libraries, which was very helpful. So that was kind of nice. That was really awesome to be able to change the code in one place and standardize it in one place, roll it out to all the boxes, and have everyone get egress or ingress network traces immediately. So as we roll this out, we have all this data, but like the thing is, it's another tool that people need to use, right? Like people are really used to using dashboards and looking at logs, but changing people's workflows, unless it's like unless it's really, really useful, it's really hard to do to get it's really hard to get adoption. So, initially we did struggle with this because tracing is very new. The UI has some ramp up. Like you kind of have to sit down and look at the traces to see what it means, and there's some terminology that you have to learn in order to get the most usefulness out of it. So what were the there were some challenges in getting adoption, and this is how we kind of tackled that. One is to get it integrated into people's workflows as much as possible. So everyone knows dashboards. That's the main tool that they use. And so we added these little dots that correlated a trace with that dashboard. So like, for example, if there was a spike in 500s, you could click on this dot, and it would send you a link to a trace that was representative of the errors that you were seeing. So if you see high response times, you'll see a trace with that latency, and then you can start debugging right away. And so giving people that context was pretty powerful. The second thing we did was add it to PagerDuty. And so when you get a page, and if there is a trace available, we'll add it into the details. And what's nice about this is like when you're woken up in the middle of the night, you just want to know what the root problem is and like mitigate it as quickly as possible. And this was pretty useful versus before you have to look at logs and sift through a bunch of error logs. You can look at the trace, you can see if it's your service or not. Sometimes it's not your service, and you could reallocate that page to the owner of that application, or like you realize it's not, it's like a new feature that's being launched and it's not a big deal, and you could snooze. Yeah. And so the big takeaways for this is that like integrating with Envoy was the biggest win, because that way we didn't have to get engineers to edit their code. You could achieve something similar with libraries, but like that zero-touch experience is really nice, especially if you're supporting multiple languages. Maintaining libraries for multiple languages is very difficult, so to minimize that effort was a huge win. Secondly is like tying all the tooling together as much as possible is also really essential for adoption. So people are used to metrics and dashboards and seeing logs. So if we're trying to come up with solutions where we could tie tracing into those tooling already and so that they could take that context from the dashboard into the tracing tool. And we also have a way we're working on a way to display tracing with the log associated with it. The sampling, that's a little bit harder, but it is possible to like be able to show the log that was emitted and link to the trace that is associated if it's available. And the second, the last thing is that like as you scale, you have to start thinking about sampling because there's just too much data to store. And sampling strategies are really hard. Especially, it's very business dependent and what data and it's dependent on like what your engineers need to triage and debug. And there's no like one bullet answer to say that you should sample based upon this. And also you can't just sample randomly, otherwise you'll get incomplete traces. So sampling strategies are very hard, and it's very business dependent, and it's something we're still figuring out. So yeah, that is the end of my talk. I just feel like I scratched the surface, and there's like so much more information I wanted to stuff in here, but felt like it would be way too long. So the place I linked here, there are a couple of links I think are pretty useful to branch out. One is the Open Tracing homepage, which has useful documentation and has a great explanation of like the vocabulary and like more detailed information about the Open Tracing specification. The second link I link is a tutorial where Yuri goes over. He's the creator of Jaeger, and he also created these like tutorials where you build a little microservice, you add instrumentation, and you kind of look at the actual data and see what data is getting emitted, and you have a deep understanding of like how it all fits together. Secondly is thirdly is the Dapper paper, which is the tool that Google uses, and this is what all this distributed tracing tools are based out of. It's a very it's not a academic paper. It's very practical, and it's a pretty fun read if you have the time to see where it all originated from. And lastly is it's a talk by Peter Alvaro, which I found really useful, where you could take tracing to the next level of like where to do chaos engineering, where to inject fault next using tracing data. So that's it. Thank you so much for coming to my talk. Feel free to ask questions to me on Twitter. I love talking about tracing and love to hear how you use it, or like if you have questions about integrating with it. And feedback is always welcome for my talk. So yeah, thank you so much.